Thank you very much, and I am very honored to be here. Giving a lecture at the Stanford University is a once-in-a-lifetime event, so I'm very excited. I'm going to talk about the preferred networks and its values, how we are going to make changes in the society, and from the AI and deep learning perspective. Richard gave you some introduction about me. As he said, I spent 26 years at IBM Research. I spent almost 1 year at the Canon. So I spent my time in US-based global company as well as a Japan-based global company. And also in academia, now I am in a startup company. My background is a computer science, but in addition to that, I have some management experiences. So from that perspective, I'm going to talk about deep learning and how preferred networks is managing these technologies to make the biggest impact onto the society. The company Preferred Networks, sometimes we abbreviate as a PFN, and I don't know why F is there, but Preferred Networks is founded 4.5 years ago. Before that, actually, our co-founders started the previous company called Prferred Infrastructure about 11 years ago, while they were as a graduate student at the University of Tokyo. We have an office in Tokyo, and we have a small offices in Berkeley, California. The current number of employees is about 180 people. Most of them, I would say 170, are the engineers and the researchers. When I joined the company 2.5 years ago, there were about 40 people, so we are growing very, very quickly. We have big investors like an NTT, Fanuc, Toyota, and recently we have investment from Hakuhodo, the big PR company in Japan, Hitachi, Mizuho Bank, Mitsui is a trading company, and Chugai Pharmaceutical is a part of a Roche, so it's a big pharmaceutical group of companies, and also Tokyo Electron is a semiconductor equipment company. We have no venture capital investment to us. That is because of our co-founders' policy that they need to keep the freedom of whatever they want to do. Our focus is distributed deep learning and applied to certain areas, and I'm going to talk about that. But before that, I want to you to understand the clear differentiation between AI and deep learning. So let me start with AI. So there are several different approaches to intelligence. So there are many different disciplines like neuroscience, brain science, approaches to study the brain by observing the brain activities. Psychology studies the human mind by observing the human behaviors. In economics, of course, they need to model human behaviors, and they use mathematical models such as game theory and optimization and so on. In mechanical engineering, there is differential equations, so they do the control theory based on these mathematical models. And then computer science is approaching to intelligence by mimicking the human intelligence. So there are many different ways to approach the human intelligence. At the beginning of the AI history in computer science, first people thought about what intelligence is. And one of the things that they thought is that the intelligence maybe do a complex mathematics. So doing the mathematics like this is integral of a mathematical formula. By the way, this is integral sign. At that time, there was no tech, so you have to write the integral sign by combining the ASCII characters. But this was a very successful AI applications in the early days. I cannot do the mathematical integral computation calculation by myself, but it does very well. Another study was natural language understanding, because people thought that intelligence means that you can use language. So this is one of the early attempts to do the natural language understanding, and the Professor Winograd is here now. At this moment, at that time, he was in the MIT Media Lab, and I remember myself that I read his PhD thesis, and I was very excited, and this is the area that I wanted to work on. So his system called the Shudo is to simulate the robotic environment, and it understands the human language, and based on the human language input, it does things like if you say pick up a big red block, you may notice that there are two red blocks, and it understands you are meaning that the big one over here, and to move this block, you need to remove the green one first, and so on. So this is a very, very intelligent system, and it was very successful. But it was in 1970s, and we don't see much advances after that. Some people thought that the intelligence is to play games against the human experts. So in 1997, IBM Deep Blue beat the Kasparov, who was the chess grand champion. And as you remember, the Google AlphaGo beat the East Saddle in 2 years ago. So these are the successes of artificial intelligence. But if you look at the technologies, AI technologies, by piece, then you may notice that these technologies will be incorporated into the daily computer science. So the first wave of AI was like 1950s and 1960s. And at that time, the focus of AI research is, for example, symbolic processing, because at that time, computer means to calculate numerical calculation. People started to think about symbol processing, and for that, McCarthy developed a programming language called the Lisp. Also, there's a lot of studies regarding the search algorithms like means and analysis. If I want to go to my home in Tokyo from here, then if I calculate my path going out of this building and make a right or make a left and so on, then I will never get to my home. The mean and analysis says that if I want to go to the Tokyo, then the longest leg should be determined first. So, flying from San Francisco airport to Tokyo, and then going to the sub-problem, which is to go to the San Francisco airport from here. So that's called means and analysis, and it was a hot topic in artificial intelligence. But nowadays, you use Google and Uber and whatever to look for the path, and it is no longer called AI. So things like garbage collection or search algorithms or language parsing, these were the AI technologies before, but it's no longer AI. The second wave of AI was focusing on things like knowledge representation or expert systems, ontology and those kind of things. And as you know, these concepts are now part of, for example, class hierarchy of the object-oriented language or modeling language or semantic web and things. So I argue that the third wave of AI, whose focus is statistical machine learning or deep learning now, these technologies will be part of the daily computer science in the future, and people will not say that this is AI. Okay. So AI means many different things. Okay. For the researchers, of course, there is a research field called artificial intelligence. But the focus technologies are different from time to time. Corporations, AI means something that uses some of the technologies, like a search or knowledge representation and so forth. So AI speaker uses speech recognition. AI microwave oven uses some heuristics to do the cooking, and the AI air conditioners detects the human beings in the room and optimize their operations. And then there is general public for which sometimes AI means human-like robots, like HAL 9000 in the movie, Terminator, Cylon in Galactica, and Astro Boy, it's a Japanese cartoon. So AI means many different things based on the context. And especially, I'd like you to distinguish between generalized AI and specialized AI. There was an interview article in Wired magazine 2 years ago. And Mr. Obama said that there is a generalized AI and a specialized AI, and we make distinctions. I don't know if the current administration understands this distinction or not, but he said that generalized AI is a sci-fi. So it's we have to make sure that what we are talking about. Okay. So from now on, I'm not talking about AI, but I'm specifically talk about deep learning or statistical machine learning. Okay. So what is deep learning? Well, in a single sentence, deep learning is a function. So function means that it takes an input and it generates output. That's simple. Okay. Usually, we have a very large dimensional variable as an input. So if you do the image recognition, like 100 pixel and 100 pixel, which means you have the vector with the 10,000 elements in it. Okay, so it's very high dimensional data, but it's just an input. And the output could be very simple. If you detect, cat or airplane in the picture, then you have probably 2 bits as an output. One is for airplane, and one is for cat. If you want to generate some images as an output, then the image output could be also very, very high dimensional. But that's it. It's just a function. Okay. When you build a function by using the traditional programming, what do you do? Let me give you an example using this as a very, very simple example, which is to convert Celsius to Fahrenheit. So the traditional way of doing the programming as a programming a function is to start with the specification requirements. So here is the input, here is the output, and then you translate this requirement to a model. So by model, I mean that there is a mathematical relationship between input and output. And usually you use known knowledge about the input and output relationships. So in this case, this is the model. Okay, and then once you get the model, then you construct the algorithms to calculate the model. So, you use a priori knowledge to to do the modeling. So the fundamental assumption here is that you know the model, okay? And also the algorithm to compute the model is constructible. So these are the prerequisites for doing the conventional programming. On the other hand, the statistical modeling approach is to do like this. So converting from Celsius and Fahrenheit, I buy two thermometers, one in Celsius and one is in Fahrenheit, and I read these thermometers from time to time and get this kind of data set. And the question is, what is the best way to simulate this input and output relationship? And that's what we do in statistical modeling or statistical machine learning. Statistical machine learning is basically the same thing as statistical modeling. So it's known for a long time. So for this kind of things, it's very easy for you to do this kind of modeling. So this is called regression, linear regression. So linear regression is actually a part of machine learning. Okay. But then traditional statistical modeling has one limitation, which is that you have to determine the model family in advance. So let me take this example. So this is the training data set. And the question is, what is the model that is going to approximate this input and output? So if you select the linear model as a model family, then you get this. Okay. If you assume that the cubic function, then you get a better approximation. Well, if you have a larger dimensions in the polynomial function, then what you get is like this. And this is known to be overfitting in a statistical modeling. And this is the difficulty of the statistical modeling. You have to define the model family which is powerful enough to represent a training data set, but not too powerful to be overfitting. Okay, so that's the challenge. On the other hand, if we use deep learning, I created a very simple deep neural network and trained this neural network with the same input data set. Okay. And this deep neural network has two internal layers, and each layer has 10 nodes. So there is, each link has a weight parameter. So this model has 141 parameters in total. And from the common sense of the traditional statistical modeling, because there is 141 freedom and degree of freedom, and the input data or training data has only 50 points, so it must overfit. But somehow, deep learning does the good approximation without too much overfitting. And this is the biggest difference from the traditional statistical modeling with the deep learning. How deep learning is powerful is also a very interesting question. And the deep neural networks usually have millions of parameters, which means it can approximate any high-dimensional function. So in a sense, it is a third Turing complete. I mean, by that I mean that for any functions, there is some deep neural network that can approximate the function to a certain error. How the deep learning is trained is there is a very good video by Jan LeCun, who is the CTO of Facebook. Unfortunately, this video is not available, but the idea is like this. Suppose that you want to create a deep neural network which detects whether the input image is a car or a dog. Okay. So there is a small two lamps for the car, and for the other one is for the dog. And you show the car picture, and you want this box to light the car lamp. But of course, at the beginning, the box does not have any knowledge about a car or dog. So what we do is to show one image, car image, and there's probably the car lamp does not light. So in that case, there's many dials, and you adjust the dials so that the car lamp lights brighter and brighter. Then you show the dog image and make sure that the car lamp is off and the dog lamp is coming brighter and brighter, and so on. So you repeat this kind of a procedure for many, many times. And after that, this box understands that which is car and which is dog. Okay, and the difference from this simple model is that the number of dials are like millions or tens of millions typically. Okay, and also you have to show the same image again and again for many times. So you use lots of computation, lots of try and error, but after that you get trained model. And with this model, what can we do? So this is one example that we are working on, which is for the autonomous driving. This is the input image, and this is the output. And for each pixel in the input image, we determine that this pixel belongs to the drivable surface or sidewalk or other cars, trees, and so on. There is 25 different classes in this example. But you can think of the car and the dog box for each pixel. In this case, there are 25 different lamps in the box. And there are so many boxes in this example. So it's just scaling of the simple model to this large system. But of course, there is a catch, which is to do this, you have to create a training data set. So this is an input, and this is the ground truth created by human being. Okay, so we prepare the ground truth training data for thousands or tens of thousands of images. Okay, and using this as a training data set, we train the neural network, and finally we get this. Okay, in a sense, this problem, taking this picture and generates that this pixel belongs to the drivable surface or sidewalks. This is a function, okay, but you cannot give the model. You cannot mathematically describe that this is, if this mathematical property holds in this input image, then this pixel is a drivable surface. You cannot do that. So in this case, the model is unknown. But you can provide the examples. Okay? And for that kind of applications, deep learning can solve this problem. The second example, or similar example, which is this is a video that when we participated in the Amazon picking challenge, the task is to specify the object from the shelf. Okay, Amazon warehouse is very highly automated, but picking the object from the shelf is done by human being because this is known to be very, very difficult. The difficult part is to understand where the specified object is, and we take the pictures. So we put randomly many items in a shelf, took pictures and annotated these pictures by hand. Okay. With thousands of these training data sets, we trained the deep neural network. And after that, we very accurately identify where the object is. Okay. So actually, so we won the second place in this competition. Again, in this case, model is unknown. So, what is the mathematical relationship between this picture and this pixel belongs to a water bottle? The third example that I can give you is the voice control.
Sure, I'll work on that.
Can you make a volume higher?
Sure, I'll work on that.
Okay, let me go back. これはどうやると戻るんだっけ?
Can you move the brown fluffy thing to the bottom?
So in this case, she's using the human voice to control the robot.
Work on that.
So top and the bottom is actually in an operator's perspective. So this side is the top and this side is the bottom.
To the left. Sure, I'll work on that.
So in this case, she said tissue box. She's going to use a different expression to
Can you
refer.
move the white and blue box to the right? Sure, I'll work on that.
So how did we train this model? Well, this is the top view of the situation.
Can you move the orange
And we showed this kind of image to human beings
Sure,
and
I'll work on
asked,
that.
what would you say if you want to move this object over there? And we crowdsourced this data collection, and we collected tens of thousands of example sentences and used these sentences to train the neural network. So there is no
Sure, I'll work on that.
understanding of natural language sentences. It's just giving the examples. And again, we cannot specify the mathematical relationship between the input sentence and the operations. Okay. So here, the model is unknown, but we can generate examples. So that's where deep learning can help to create a solution. The second way to use deep learning is where, even though the model is known, but still the algorithm is not known. Okay, this is an example of coloring the line drawings. So left-hand side is the input, the line drawing, and our deep neural network automatically make the colored version of the image. And sometimes you can put the hints. So I want this part in red and so on. The interesting thing is, how did we train this model? Well, we collected a lot of colored images from the internet, okay? And we applied edge detection algorithms, which generates line drawings from the colored image. It is known algorithm, and from here to there is a known algorithm. So we applied edge detection and generates a lot of pairs of line drawings and colored image. And using this as a data set, training data set, we train our deep neural network. So in this case, the relationship between the colored image and line drawings. It's if you apply edge detection, then you know that. But you don't know the reverse function. Okay, and so deep learning can use for that kind of applications. Another example that I can give you is to control machines. So this is an example that we showed at the consumer electronics show 2 years ago. This is autonomous driving demonstration. This is not the real cars. This is a model cars. Inside it's Lego Mindstorm. But silver cars are controlled fully autonomously by deep learning. Red car is operated by our vice president. He's controlling manually, and he's not good at driving the car. He's hitting and also doing nasty things against the other cars. But you may notice that the silver cars are very good avoiding the hitting other cars. So the question is, how did we train this model? Okay, in this case, you can specify the mathematical constraints. The car moves, and you should not hit each other. So it's a very simple mathematical statement. But how you control the cars is not easy. Okay, so let me show you the video. So the way it is trained is to use the so-called reinforcement learning. We use a simulator. If you look at the car in a circle, this car has a simulated virtual sensor beams to 32 different angles and get the sensor input. So these are the sensor input, and this is the output, which is to accelerate or move right, move left, or to back up. And so there are only a 5-bit of output. And the input is 256 sensor input, plus some other current situation of the car, and total 273 input dimension. The car will get a reward if it makes a forward movement, and it gets a penalty if it hits other cars or hit the walls. And we use deep learning to calculate from the input to output, and based on the reward penalty teacher signal, it adjusts the many knobs and so on, and try to learn how to drive. So at first, it just do a random movement, but then by doing the random movement, sometimes it go forward and get a reward, and parameters are adjusted, and from the next time, it now knows moving it forward is a good thing to do. And finally, it has a smooth movement, and probably you notice that the car is moving outside of the curb. We did not tell the cars to do that, but by doing a lot of try and error, they notice that moving the outside of the curve gives a higher velocity, and which gives a higher reward. And that's why they learn to do that. Okay. We did a similar thing for drone, and in this case, the task is to capture the virtual flag, but you cannot move across the hazard, which is represented by the red bars. Yellow bars is a pre-warning signal for the red bars. And we apply the same technology, so same reinforcement learning, so give it a reward when it gets the flag and give the penalty when it moves onto the hazard. Now, the difference between this and the previous one is that, of course, we use a simulator, but in this case, drone case, the simulator does not reflect the real behavior of the drone because drone has a lot of influences from the walls or some air movement in the room and so on. So what we did is to create the two neural networks. One is to control the drone, and the other one is to predict the movement of the drone by observing this drone movement. So with that, we finally get a good control of the drone. Okay. So these are the examples of deep learning, but there is a challenge for deep learning, which is the computational load. As I said, there's a lot of parameters, and we have to do a lot of iterations about the training. So this is a rough estimation by our VP, and this is the assumption that to finish a training using 1 gigabyte of a training data set within 1 day requires 1 teraflops. And with this assumption, for example, for the image recognition, probably we may need 10 petaflops or 10 exaflops. The life science has a lot of data, and we have to have a larger computational power. Speech recognition, autonomous driving, these real-time sensor applications generates lots of data, and we have to have lots of computation. And this is a challenge, actually, that's a challenge for the deep learning. And that's where we developed a technology called the Chainer, which is a scalable deep learning framework. By framework, I mean it's a kind of programming language. With that, you can create a deep learning application easily. Well, the Chainer was originally developed with flexibility as an objective because in the deep learning area, there are, it's moving very, very quickly. There are many papers published every week, and we have to try these ideas to understand this technology is good for our application or not. So that's why we had to develop a Chainer with the flexibility in our mind. But as I said, also the computational time is very, very important. So we shifted our focus to the scalability of our framework, Chainer. And with this Chainer combined with our in-house supercomputer, we achieved the world record of the deep learning training. The ImageNet training is one of the standard benchmark for the deep learning training performance. And this is last December, so this is in a heavy competition, so other companies are catching up. But at that time, we were the number one. So we successfully completed the ImageNet training in just 15 minutes. Previously, it was 1 hour or 30 minutes. We spent a lot of money on purchasing this supercomputer infrastructure, which has 1,024 Pascal GPUs. And the list price of a Pascal GPU is $10,000 US a piece. So you can do the math, how expensive it is. By the way, this supercomputer was ranked as the 91st in the worldwide supercomputer ranking. And the companies like us, it's a small company, has this kind of computational structure is extraordinary, I believe. But that is one of the strengths that we have, how we differentiate ourselves from the others. Similar things is done just 2 months ago, which is about Google AI Open Image Challenge, and we were the second place again, but the difference with the top one is very, very small. So we are one of the best. And we used a newer supercomputer which has 500 Volta GPUs. And we use the chainer multi-node, which gives the scalability of the computation. So we add more GPUs, we get a higher speed. So these are about the deep learning. So the deep learning can do many things, but you need a lot of computation. In addition to that, there are fundamental limitations of deep learning, and I want you to understand this, because deep learning is not a silver bullet. It's just a mathematical formula. Well, the first limitation is that we train the deep neural network using the data observed in the past and do the predictions in the future. Okay, so fundamental assumption here is that the deep learning assumes that the future is the same as the past. Okay, at least in a statistical distribution point of view. So that's the first limitation. The second one is, even though we can assume that the future and the past are the same in terms of the statistical distribution, still the training data set is finite, which means there are many points which are not covered in training data set. If that point is somewhat close to the points in the training data set, then you can make a very good prediction. So it is called the interpolation. But if the new input points are not anywhere near to the training data set, then deep learning or statistical machine learning is powerless. So sometimes customer comes to us and please create a deep neural network to deal with very rare cases or emergency cases. But it is not possible because we don't have the training data set. Okay. So that's the second limitation. And the third one is that this is fundamentally statistically. So which means we always assume that there is some original distribution, probability distribution. And probably it is not known, but we assume that you randomly sample from this original distribution and create a training data set. Once you get the training data set, you can train your neural network. But the problem is that in this first phase, which is the assumption that you are doing the random sampling from the original distribution. IID means that the independent and identical distribution. Okay, so that means there is always bias in the sampling. Okay. Well, suppose that you throw a dice 100 times. Is there a chance that all 100 times are 1 or 6? Okay. Well, it is very, very unlikely that all the 100 times are 1, but you cannot guarantee that it will not happen. So that means, the training data set has always some bias. And there's no way that you make a 100% guarantee about the accuracy of the training, the deep neural network. So this is, I think, the most important limitation of the deep learning, or more generally, statistical machine learning. Okay. So let me recap what is deep learning. So deep learning is just a new way of programming, a new way of programming a function, but no prior knowledge on model or algorithm is necessary. Preparing a data set is the key to do this kind of a programming. And creative thinking about how you provide a teacher signal. The teacher signal could be provided by the human annotators, but could be supplied by reinforcement learning using simulators, or could be done by some other ways. So creative thinking gives very, very innovative applications. It requires a lot of computation. And also, this is fundamentally statistics, which means there should be the training data set must be the IID, and it gives the approximation only. So there is no guarantee of the 100% accuracy. So that's the deep learning. Okay, so let me talk about the third topic, which is about our company. Okay. So we are specialized in deep learning, and if you look at the deep learning landscape, many players in this quadrant, which is to deal with the cyberspace data like text or image on the internet, and facing the consumers to provide the services. But we are more interested in physical world because it generates lots of data, and also we are facing mainly B2B companies like Toyota and Fanac. So that's our business. But then there is a big challenge for us, which is how to do a good business in deep learning, because most of the deep learning technologies are open sourced, including our chainer. So we cannot make money directly out of chainer. Well, of course, we can think of doing the consulting for a particular customer, or doing a system integration for the particular customers. But that kind of business, well, it's easy money, but that kind of business does not scale, because we have to, the growth is proportional to the number of employees that we have. So we would have higher growth than just a linear. Also, if you put our researchers and engineers in the customer engagement, they are tied up with the customer engagement. Many of the customer engagements is actually can be done by more common technologies and not cutting-edge technologies that we have. So time spent on the customer engagement prevent us to do the more cutting-edge research and engineering. So that's the business challenges that we have. What we are doing is, first, our assumption is that the cutting-edge technologies speak themselves. So we don't have any marketing or sales dedicated personnel. 90% of our workforce are engineers and researchers. And that also, that the cutting-edge technology is the best way to attract the talents from worldwide. Sometimes people do not know our company, Prferred Networks, but many of the researchers in deep learning know chainer. So having the China as an open source technology is a very, very strategic for us to attract the people from the worldwide. Actually, about 50% of the new applicants to PFN is from outside of Japan. The second is that we heavily invest on people and on the computational resources. And that is to stay cutting edge. And then we have the current businesses, which is to work with the big companies like Toyota and Fanac to the joint research and development, and it generates a healthy profit for us. And we keep that kind of activities, but also we work with the new investors to create the new businesses. And we are continuously working on that. But that gives us the breathing space or freedom of operation. And we are looking at the new opportunities, and we don't know what the new opportunities are at this moment, but we are ready to capture these new opportunities when it arises. So the most important thing for us is that we have the technology and we have the resources when the right moment comes. That's our strategy, and that comes to our values, which means to do this, what should we do? Okay, and we had a week-long discussion by everybody in our company. We call this PFN Values Week, and everybody participated in the discussion about who are we, what we should do, how do we differentiate from others, and so on. And we came up with 4 value statements. The first one is that we are motivation-driven, which means if you are not motivated to do something, then your performance is about this level. But if you are strongly motivated to do this, then your performance will be doubled or tripled. So that's motivation-driven, and with that we have a very, very flat organization. We have the 2 founders at the top, but everybody else reports to them. And there's many projects. Some people belong to the multiple projects. People are moving from one project to another based on their own motivation. And how to manage these people, we heavily use the IT, like Slack, for example. And with that, our founders can monitor what's going on in the company and can give the right directions whenever it is necessary. So that's the first value. The second value statement is learn or die. So this area is moving so quickly that we have to be learning every day. So our co-founder, Daisuke Okanohara, had tweets about the papers he read. And this is actually a very good source of the new information about deep learning. So we have to learn and continuously do so. The third statement is proud but humble, which means we are the best, one of the best in the deep learning industry. Okay, so we know that we are one of the best, but at the same time, we know that there are things that we don't know. Okay. So known unknown is very, very important for us. So that means we have to be humble and we have to listen to others, other experts in other areas and so on. So that's the third one. And the fourth one is what we do. We do whatever other people cannot do. And that's the reason why we can differentiate ourselves. So that's why we do not get into the system integration or consulting services. These are the things that others can do. We are focusing on whatever only we can do. So that's the statement, and that's how we are prepared to capture the best moment in the business. So probably you think that it's a very different from the business model of the other startups. Probably we won't be one of the kind as a company. So keep watching us. Thank you.